what is nothing? It's an extremely, extremely difficult question to answer, because if you think about it, wherever you look around you, there always seems to be something there. Things appear almost impossible to escape from. Even just trying to imagine true nothingness seems like an impossible task. But this is more than just a philosophical question. I have here a box. What would happen if I were to remove everything I possibly could from inside it? All the air, dust, every last single atom, until there was no thing left. What then exists inside the space in the box? Is it really nothing? You might wonder why this matters. Well, emptiness is what makes up almost the entire universe. Even the atoms that make up our bodies and the physical world around us comprise mostly of empty space. This film tells the story of how we've begun to understand what is known as the void, or the vacuum, emptiness, or simply nothing. It's about reality at the very furthest reaches of human perception, a place where the deepest mysteries of the universe may be held. This film reveals how, using ingenious technology, humans have transcended their physical senses and found ways to understand and probe the universe at the smallest scales. Today, we believe the void contains nature's deepest secrets. It might even explain why we exist at all. And that's because, to the best of our knowledge, the entire universe appeared nearly 14 billion years ago out of nothing. For over 1,000 years, our understanding of empty space was defined by one man, the Greek philosopher Aristotle. To Aristotle, the concept of nothingness was deeply disturbing. It seemed to present all sorts of problems and paradoxes. He came to believe that nature would forever fight against the creation of true nothingness. As he put it, nature abhors a vacuum. These words stuck for over 1,000 years because after Aristotle, people who attempted to make empty space faced an uphill struggle. It seemed nature was indeed doing everything in its power to stop them. Well, the whole mystery of nothingness is contained inside this simple drinking straw. Let me demonstrate. If I suck out the air from the top of the straw, more air immediately rushes in to fill the space left behind. And even more weirdly, if I block off the bottom of the straw and suck, the walls of the straw collapse in on themselves. It's as though the universe won't allow me to make nothingness. And it gets even weirder. If I take a sip of my drink and pinch off the top, then it seems nature's so intent in stopping me that even the law of gravity is suspended. So it's not hard to understand why people believed that it was impossible to make truly empty space.
But there's a very simple explanation for why a straw behaves like this, a reason that would come as a profound shock to the people who worked it out. By the 17th century, some strange exceptions were being found to nature's abhorrence of empty space. And it was beginning to seem like there may be ways of tricking nothingness into existence. The man who would finally do what Aristotle thought impossible was an Italian Jesuit called Evangelista Torricelli. Torricelli's experiment would, for the first time, create and capture empty space for long enough to begin to study it.
This is how the experiment went, with a tube filled with mercury and a finger really strongly clamped over the end. The tube was then turned upside down and then placed into the bath of mercury. And at this point, the mercury was released, and you can now see it dropping down. And then it stops.
So I guess the important thing is that that isn't trapped air.
Well, we started with a tube filled with mercury, and all we did was we let it drain out.
But it doesn't drain out completely. It reaches a level and stops. Torricelli's experiment had not only created an airless space, it had also shown that the atmosphere has a specific weight. The reason my straw crumples when I suck the air out is because of the pressure of the atmosphere that surrounds it. But Torricelli's apparatus was overcoming this by using the extreme weight of mercury and a rigid glass tube. The level of mercury in his tube was a measure of the weight of the atmosphere.
And the level is, of course, determined by the weight of the mercury on the one hand and the weight of the air pressing down on the other. And so the two balance out like scales. They'd found a way to weigh the atmosphere. And Torricelli wrote this fantastic phrase. He said, "Noi viviamo sommersi nel fondo d'un pelago d'aria elementare." We live at the bottom of an ocean of air. Suddenly, the air really was a substance.
But I guess the real mystery for me now is then, what's inside here? Could this really be nothingness?
Indeed.
In revealing that the air has a weight and that it's pushing down on us all the time, filling any space it can, Torricelli had managed to create an empty space, a type of nothingness that could now be studied. Over 1,000 years of thinking about the way nature worked was beginning to crumble.
Medieval philosophy, much influenced by Aristotle, supposed, reasonably enough, that there's no such thing as empty space in nature, and yet here is a pretty simple device, a long, thin glass tube with some liquid in it, which is able to produce, says Torricelli, an empty space, thus showing that Aristotle and his disciples are wrong. How can you show that centuries of philosophical tradition are wrong just by doing a trick? That didn't seem right at all.
But Torricelli was right, and it would fall to philosopher and scientist Blaise Pascal to develop and refine his work. As Pascal began investigating Torricelli's ideas, he discovered even more peculiar properties. In Paris, he carried a mercury tube to the top of a huge tower and recorded the mercury dropping to a lower level than it had been on the ground. It seemed the pressure of the air fell as you went higher. Pascal's experiments would lead to the realization that the Earth is cocooned in an atmosphere that rapidly thins out the higher you go, eventually becoming the cold, silent expanse of space. Torricelli and Pascal had begun to unravel a profound truth. Nothing is everywhere. Our Earth is merely a tiny speck of dust floating through a vast expanse of an utterly silent, inhospitable void. Nature doesn't abhor a vacuum. A vacuum is nature's default state. So what was this vast, empty space? Now it was possible to make it on Earth. Scientists became deeply curious. What exactly were the properties of nothingness?
After Torelli and Pascal's experiments, many scientists became fascinated with studying the properties of the vacuum. And they found some very odd things. For instance, placing a ringing bell inside it became silent. You couldn't hear it from the outside because, having removed all the air, there was no medium to carry the sound waves. Most intriguingly, although you couldn't hear the bell, you could still see it.
This means light must be travelling through the vacuum. But how could it do this?
For those scientists carrying out experiments with the vacuum, there was just one simple conclusion. The vacuum wasn't empty after all. The fact that they could see inside it meant that there still had to be something left in there. Just as air carries sound waves, they believed there had to be a medium carrying the light waves. And whatever it was proving very difficult to get rid of.
The nothingness that had been glimpsed by Torelli and Pascal now appeared to be a something, a mysterious substance which carried waves of light. And if this substance existed in our vacuums on Earth, it meant that it also existed out there. It appeared once again that nothingness could not exist in nature. Everything in the universe appeared to be sitting within an invisible medium, what scientists called luminiferous ether.
It was clear for many reasons, many good reasons, that light was a kind of wave. But if light is a kind of wave, what's it a wave in? And sound waves are waves in air. Light waves are waves in what came to be called from the early 1800s the luminiferous ether, the light-carrying fluid that fills all space. If there's a fluid that fills all space, if light is a wave, nowhere is empty, because light travels everywhere. So at the very moment when it seemed absolutely plausible that, yeah, sure, there can be empty space, it's obvious that there isn't. And that there's this stuff called ether that carries light.
The problem was that this ether appeared to be so subtle and so intangible that it eluded all attempts to measure it. It wouldn't be until the end of the 19th century that an experiment would be built that was sensitive enough to reveal the truth. The experiment would take place in the United States, and Albert Michaelson, the scientist who conducted it, would go on to become America's first Nobel Prize winner. From a young age, Michaelson had relished tackling the particularly difficult practical problems in physics. He'd earned his reputation by making extremely precise measurements of the speed of light.
Having completed his work on light, Michaelson travelled to Europe to spend some time amongst some of the best scientists in the world. And it was there that he became fascinated with the topic that everyone was talking about, the mysterious luminiferous ether. One idea in particular captured his imagination. It had been proposed that if you could measure the speed of light accurately enough, then it might just be possible to actually deduce the properties of the ether.
And this is how. If there was an ether, then as the Earth orbited the Sun, we should be able to detect its presence. It will be like sticking your hand out of the window of a moving car. You feel the rush of wind as the car travels through the air. Michaelson realized that if this picture of the ether was true, then two light beams should travel at different speeds on Earth, depending on the direction they were moving through this ethereal wind. The difficulty was actually in making such a measurement. It seemed like an almost impossible task. The problem is this: the speed of light is over 186,000 miles per second. Now that's pretty nifty. In comparison, the Earth virtually crawls around its orbit. So the difference in speeds between those two light beams would be tiny, something like 1 part in 100 million. So the precision needed to get any sort of meaningful result was way beyond anything that scientists thought was possible at the time. But not so the headstrong Michaelson. He began to work his way around the problem. He started to develop techniques and precision instruments that he believed would be capable of unlocking the secrets of the ether. From 1881, Michaelson was taking measurements and tweaking and refining his apparatus. But it wouldn't be until 1887, at the Case School of Applied Science in Cleveland, Ohio, that Michaelson would finally build a machine sensitive enough to give him some definitive answers. There, he joined forces with another scientist, Edward Morley, to conduct what was to become one of the most notorious experiments in physics. The original apparatus was set in a solid block of sandstone and then suspended in a bath of mercury to remove any vibrations that might affect the measurements. It was incredibly high-tech and very expensive. Think of it as an 1880s version of the Large Hadron Collider. Okay, so here's how it works. Light is emitted from this source. In the middle is something called a beam splitter, which divides the light up into two paths. Over here are two mirrors which reflect the light back to the middle, where they recombine at the beam splitter. The light is sent down to this detector. Now, because of the wave-like properties of light, you see a very specific pattern here. Basically, if the light has traveled at the same speed along the two paths, then you see a bright spot in the middle of the pattern. So here's the really clever part. Michaelson and Morley reasoned that if the Earth really was moving through a stationary ether, the experiment should behave in a very different way. Let's look at what happens when we simulate the effect of an ether. The light leaves the detector and gets split. Now here's the key. The light that travels against the ether and back again covers this journey in a different time to the light traveling across the ether. This means that when the light waves recombine, they now interfere with each other. This interference means that the image will have a dark spot at its center. See this, and you know that the void must be filled with a stationary medium through which the Earth is moving. Now, of course, I can't be sure exactly what was going through the minds of Michaelson and Morley as they began their experiment. But it's a safe bet that, given the scientific consensus at the time, they were convinced that the ether really existed. So they'd have been sure that they would have found light traveling at different speeds as it moved in different directions. But it didn't. No matter how they rotated their apparatus, they always found light traveled at the same speed. Michaelson and Morley had gained an extraordinary and accurate result. But the idea of the luminiferous ether was so ingrained that they believed simply that their experiment had failed. So what is going on? Why didn't Michaelson and Morley's experiment reveal the result they were expecting? How could light always be traveling at the same speed? Well, the answer is simple. The ether doesn't exist. No matter what light is doing, how it's traveling, it doesn't need to be carried along by this mysterious stuff that pervades the vacuum. So how does light move through empty space? Well, by the end of the 19th century, light was known to be in fact a combination of fluctuating electric and magnetic fields. But it would take the genius of Einstein in 1905 to reveal that this picture of light doesn't need an ether. He showed that it has the weird property of being able to propagate through completely empty space. So the message from the failure of Michaelson and Morley's experiment is this: there is no ether. Maybe the vacuum is really empty. If only it were that simple. Almost as soon as Michaelson and Morley had revealed, by accident, that you really could have nothing, scientists began to discover some very weird properties of nature. In the 100 years that followed Michaelson and Morley's experiment, physics and our understanding of the vacuum has been totally transformed. But what drove this huge shift wasn't simply scientific curiosity, but the fact that in the late 19th century, the vacuum and its many applications had become big business. Industry was finding ever more ingenious ways to make money out of nothing. Understanding and harnessing the vacuum turned out to lead to a wealth of new technologies that we just take for granted today. Everything from the light bulb to the television were only made possible because they could contain within them small volumes of vacuum. The filament inside a light bulb can glow for long periods because it's contained within a vacuum. Expose it to air and it would simply burn out in seconds. As cities around the world began to electrify, the demand for light bulbs grew massively. The engineers became ever more skilled at creating cheap, efficient vacuums. This technology would give rise to a huge range of gadgets. Everything from the valves in radios and early computers to the television. But all the technological innovations that came from harnessing the vacuum would pale into insignificance when compared to what scientists would soon find out about the fundamental nature of reality. Because vacuum technology was getting so much cheaper and more efficient, scientists all over the world could use it as a tool for research. In empty space, nature's tiniest constituents could now be studied without interference from the contaminant-filled air of the outside world. This revolutionized physics. Because of the vacuum, X-rays were discovered in 1895. The following year, the electron was identified for the first time. And in 1909, Ernest Rutherford would use vacuums to help reveal the strange structure of the atom. These discoveries were all feeding into a radically new picture of the way nature works at its smallest and most fundamental level. It was a theory that would come to be known as quantum mechanics, and the submicroscopic world it describes behaves very differently to the world we're used to. This is a world where, against all common sense, it seems impossible to ever truly have nothing. This is the classical world. Action and reaction. Cause and effect. It's sensible, certain, and knowable. But the quantum world soon revealed itself to be very different. There was one discovery that was particularly troubling, and it's known as Heisenberg's uncertainty principle.
In everyday life, we use to doubt, to uncertainty. How can we be sure that something is this way or that way? Well, it turns out that nature itself is based on indeterminacy, in uncertainty. The world of quantum physics, the microscopic world, is a world of uncertainty. It's a world where you can never be sure of what's going to happen. Not because your measurements aren't good enough, simply because at a very fundamental level, nature itself is based on uncertainty.
Okay, I'd like to try and get across the essence of Heisenberg's uncertainty principle. I'm going to use a non-mathematical analogy. Now, we have to be careful here. It is just an analogy, so we shouldn't push it too far. I have here two identical memory sticks. On the first one is a high-resolution image. It's a picture of me having a game of pool. We can see it's very detailed. In fact, I can zoom in even quite closely onto the pool ball. And you see, even at this magnification, I can still see the precise position. I can see the edges of the ball very detailed. But what I don't know is how fast the ball is moving or what's going to happen next. Now, on this second memory stick is another file. It's a very different kind of file. It's a movie. The important thing to note is that the file is the same size as the high-resolution image. Now, have a look at this. Now we can see the whole movie playing out. It's the same scene, but you can see all the balls moving. But if I zoom in on some detail, very quickly the balls become fuzzy and blurred. So for the same amount of information, although I've gained knowledge about how the balls are moving, I've lost information about their exact positions.
So the more I know about where something is, the less I know about how it's moving. In the quantum world, I cannot, at the same time, know both these quantities exactly. Unfortunately, there's no way around this. Heisenberg showed in his mathematics that this is an inescapable feature of reality at this scale.
Okay, so what has all this quantum weirdness got to do with nothing? Well, you see, Heisenberg's uncertainty principle can be expressed in a different way, in terms of a balance between two other quantities, energy and time. Now, this is going to sound quite complicated, but it's very important, so I'm going to try and explain. You see, if I were to examine a small volume of empty space inside this box, then I could, in principle, know how much energy it contains very precisely. But if I were able to slow time down, things would start to get very strange.
Okay, so we're now looking at a tiny interval of time that has been stretched out. Heisenberg's uncertainty principle tells us that because I'm looking at a smaller interval of time, I've lost precise information about the exact energy in the box. If I could examine an even smaller interval of time and an even smaller volume inside the box, then Heisenberg's equation suggests something truly bizarre could happen. I will be so uncertain about how much energy there is in that part of the box that there's a chance it could contain enough energy to create particles literally out of nowhere, provided that somehow they went away again very quickly. Heisenberg's uncertainty principle seemed to suggest that in truly tiny amounts of time and space, something could come from nothing. But then what? If particles could pop into existence, where do they go? Why don't we see these particles appearing all around us?
The vacuum, contrary to what one normally expects from the vacuum, is alive. It's alive with what physics call quantum fluctuations. In the vacuum, little packets of energy appear and disappear very, very quickly. And this is perfectly allowed by the laws of physics. It's so allowed that it has a name. It's called Heisenberg's uncertainty principle, which tells us that you could borrow energy from nothing so long as you pay it back quickly enough.
The vacuum is alive. Bizarre though these ideas seem, they are, I promise you, fundamental to our universe. To see how this can be, our story of nothing takes us to one of the most gifted and oddest characters in the whole history of physics. Behind me is Bishop Road Primary School in Bristol, and almost 100 years ago it was attended by two students who were destined for greatness. One of them, Archibald Leach, would go on to conquer Hollywood, becoming better known as Cary Grant. The other was a quiet, shy and rather intense boy 2 years younger than Grant, who would become one of the greatest scientists Britain has ever produced, the theoretical physicist Paul Dirac.
Even by the standards of theoretical physicists, Dirac was a very queer bird. He was not someone you'd go for a beer with. Intensely focused, man of extremely few words, very, very little empathy, and someone of rectilinear thought.
These personality traits were key to Dirac's genius, but they often resulted in difficult or awkward social situations with his peers. Even in casual conversation, Dirac would never speak unnecessarily. He'd often leave these long pauses in between sentences while he worked out the most precise and concise way of expressing himself. Friends jokingly coined the term a Dirac, which stands for the smallest number of words it's possible to speak in 1 hour while still taking part in a conversation. It's a sort of unit of shyness. Dirac's unusual personality had its roots in a difficult and troubled childhood. But from a young age, he'd found solace in the classroom. In particular, he excelled at both mathematics and technical drawing.
This was something that cultivated his visual imagination. In math classes, he was looking at mathematical symbols, he was looking at similar things, but in a geometric way in his technical drawing class. Now, it's very, very, very suggestive of the way he looked at physics later on, because Dirac always stressed that he was preeminently a visualizer. He was someone who had a geometric look at physics. He was not interested per se in mathematical symbols. Rather, he wanted to have a visual sense of what was going on in the mathematics.
Dirac continued his visual training, doing a degree in engineering before going to Cambridge to study mathematics. It will be here that Dirac would begin to unravel the deepest mysteries of the vacuum and uncover what was really going on in empty space. But his insight sprang from a seemingly unrelated difficulty.
By 1928, physics was struggling with a big problem. The two most important theories that describe how the universe worked didn't agree with each other. On the one hand, you had Einstein's special theory of relativity encapsulated in the famous equation E equals mc squared. It was a beautiful, simple, and elegant theory that describes the behavior of things close to the speed of light. On the other hand, you had Planck's discovery of the quantum and the revolution that followed, describing the bizarre rules of the very, very small.
The problems arose when trying to describe situations where things were small enough for quantum effects to be felt, but traveling fast enough for special relativity to be important. Specifically, there were huge problems trying to describe the electron, a tiny particle whizzing round inside an atom. If both these theories were true, then they should be able to be used together to give a mathematical description of the electron.
But what if this couldn't be done? What if quantum physics and special relativity couldn't be married? This would mean one or other of these two cornerstones of physics had to be wrong. A way had to be found for the two theories to be married together. And it will be Dirac who would achieve this.
Dirac's unification of the special theory and the rules of the quantum world would rank as one of the greatest mathematical accomplishments of the 20th century. And it would lead, inadvertently, to a radical new picture of nothing. To get a non-mathematical sense of what he did and how he did it, I've come to the cinema to see one of Dirac's favorite films, 2001: A Space Odyssey. Understanding why it appealed to him helps give us an insight into how he managed to solve this great problem.
If you look at 2001, it was, as Kubrick has said, it was a demonstration that you could make a really good movie script without words, but with the power of visual imagery. Now, that in some ways is very closely analogous to Dirac's theoretical physics, because for him, what was central were the mathematical equations. And moreover, he had a visual sense of what those equations meant.
The abstract images of 2001 appealed to Dirac because they captivated his brilliant visual imagination. And it was this highly developed and unusual way of thinking, honed in his school days, that would enable him in 1928 to visualize a unique way of describing the electron. It was a description that finally managed to unite Einstein's special theory of relativity and the weird world of quantum mechanics. Today, it's known simply as the Dirac equation. It may look like a small collection of symbols, but to a mathematician, this equation is profoundly beautiful. A complex and symmetrical synthesis of mathematical ideas expressed with stunning clarity. This is the commemorative plaque at Bishop Road, Paul Dirac's primary school, and on it, his famous equation. Within these few symbols lie profound truths about the universe. But don't be deceived by its apparent simplicity. Think of this equation as the tip of a giant mathematical iceberg. Each of these terms relate to entire branches of mathematics and the particular relationships between them. Beneath this equation are mathematical ideas that have been developed and honed by many, many other great individuals.
If you think of a poem, you can think of it as the most supercharged kind of language, the way you compress meaning into a very, very brief area on the page, right? Dirac was producing equations that had that kind of concision, and you can then unpack them, just as you reread a Shakespeare sonnet and see more and more in it, more and more elegance. Same with the Dirac equation. You find an equation there, and you can keep finding things that that were not obvious on first reading. In fact, Dirac actually once said that the equation was smarter than he was because it actually gave more stuff out than he put into it.
There was one particularly odd thing that the equation seemed to be saying to Dirac, something that would redefine the concept of empty space forever. In his description of the electron, Dirac had been forced to use a collection of 4 equations represented by the symbol gamma, in order to make special relativity and quantum mechanics fit together. But the need for 4 equations seemed strange. To Dirac and other physicists in the 1920s, the first 2 were quite recognizable. They described the behavior of an electron as it had been observed in the laboratory. But the second 2 were very strange. They seemed to be saying that there was some other type of electron that could exist, one that had never been seen before. So this is the normal world we're all familiar with. And here, scaled up many, many times, is a regular electron, of the type contained within the trillions of atoms that sort of make up this table, that make up me and everything else in the universe. Now, Dirac realized that these mysterious new elements in his equation predicted the existence of a strange new kind of particle, in some ways just like the electron, and yet at the same time very, very different. Dirac gradually became convinced that the new parts of his equation were describing something that could be thought of as an anti-electron. In many ways, it was like the mirror image of an electron, having opposite properties like electric charge. And in principle, an anti-electron could form part of an anti-atom, and many anti-atoms could fit together to make an antimatter table, or even an anti-me. But the weirdness didn't end there. Dirac realized that if things and anti-things ever met each other, they would instantly annihilate, turning all their mass into energy, disappearing completely. Here, finally, was the answer to the riddle of empty space. Heisenberg's uncertainty principle had suggested that matter could pop into existence for incredibly short periods of time. Now, Dirac had provided the mechanism by which matter could be created out of the vacuum and just as quickly disappear again. So let's take another look at our box. Whenever a particle pops out of empty space, so simultaneously does its antiparticle. Although this sounds completely ridiculous, let me assure you that it is true. So whenever you try to remove everything you can from empty space, it's still always awash with all these fluctuations. Within nothingness, there's a kind of fizzing. a dynamic dance as pairs of particles and antiparticles borrow energy from the vacuum for brief moments before annihilating and paying it back again.
Dirac's theory of the electron and the idea of antimatter gives us a completely new picture of the vacuum. Before, you could think about the vacuum as just empty space, so to speak. Relativity had said you don't need an ether, so the picture was of the vacuum being empty. But when you bring relativity and quantum theory together, then you have, for certain, this notion of electron and anti-electron pairs just appearing out of the vacuum, right? So you can think of these pairs just sprouting all over the place in the vacuum. So the vacuum goes from being nothing to being a place absolutely teeming with matter-antimatter creation.
Dirac's ideas about empty space were refined and developed into what is known today as quantum field theory. And these strange fleeting things within nothing became known as virtual particles. So it seems nothingness is in fact a seething mass of virtual particles, appearing and disappearing trillions of times in the blink of an eye. I've come to Imperial College London to see the effects of these virtual particles myself. Thanks to a brilliant experiment by an American scientist called Willis Lamb, we now have a way to conclusively show that there is activity within apparent nothingness. But in order to glimpse it, you have to peer deep within a single atom. Amazingly, Lamb found an ingenious way to do this. So what did Lamb do? Well, his experiment relies on the quantum rules of the atom. Within atoms, electrons have very specific discrete energies in the way they orbit around the nucleus. His experiment showed that if the vacuum really was full of these hidden fluctuations, then these would cause the electron's orbit to wobble ever so slightly. Think of it as an analogy, as though the electron is a plane flying along and hitting some turbulence, forcing it to move up to a slightly higher altitude. So this is how the experiment works. Contained within this vacuum chamber are a small number of atoms. While Lamb used microwaves in his original experiments, in this version, the team at Imperial are using lasers to probe the electrons.
Now, if you think this all looks very complex, just remember how small a measurement it is we're trying to make here. This apparatus has to be sensitive enough to pick up minute changes in the behavior of something that is itself extremely tiny. Imagine we could scale up the wobble in the electron that's being measured to the size of this apple. That would mean that this vacuum chamber behind me would scale up to being 1 trillion miles in size. The vacuum chamber will be something like 100 times the size of the entire solar system. It would take light about 40 days just to travel from the top down to the bottom.
So what is going on in there?
Okay, so let me first fire up the laser in the experiment behind me. Now, what this monitor will show us is exactly what's going on inside the vacuum chamber, down at the minutest scales. Now look at this peak that's appeared. It may not look very exciting, but it's telling us something really remarkable, because this is measuring the amount that the electron is being wobbled about by the vacuum itself. If the vacuum were truly empty, this peak wouldn't exist. We'd just get a flat line. What this is telling us is that however hard we try to remove everything we can from space, we can never get it truly empty. Everywhere in the universe, space is filled with this vacuum that has a deep, mysterious energy.
But it doesn't end there. When using the mathematics laid out by Heisenberg, Dirac, and others, you can calculate the amount that the electron should be affected. When you run the real physical experiment, the answer you get matches the theory to 1 part in a million. The theory of quantum mechanics is the most accurate and powerful description of the natural world that we have. But there's a much more dramatic way in which we can see the effects of these quantum fluctuations. And that's because they're written into the stars. Today, our best theories tell us that as the universe sprang from the vacuum, it expanded very rapidly. And this means that the rules of the quantum world should have contributed to the large-scale structure of the entire cosmos.
When our universe first came into existence, it was many times smaller than a single atom. And down at this size, it's governed not by the classical rules we're familiar with, but by the weird rules of the quantum world. This is, for me, one of the most profound and beautiful ideas in the whole of science, that it's quantum reality that has shaped the structure of the universe we see today. Our universe is just the quantum world inflated many, many times. Nothing really has shaped everything. And what's more, we now have a way to see this.
This is a picture of the first light that was released after the Big Bang. Think of it as a baby photo of everything. This incredible picture was taken by the WMAP space mission team.
This is like taking a picture of an embryo that's 12 hours after conception compared to taking a picture of a person who's 50 years old, right? It's in the same perspective, right? And, at 12 hours, you may have 2 cells. I mean, this is very, very early in the universe. And yet we're seeing what's equivalent to the DNA, the blueprint for how the universe is going to develop.
With the help of highly sensitive satellites, the WMAP space mission team were able to study this image of the embryonic universe in amazing detail. And when they did, tiny variations in its temperature were revealed. It soon became apparent that the tiny differences in temperature are in fact the scars left by the quantum vacuum on our universe. These irregularities, created in the first moments of existence by the teeming quantum vacuum, meant that the matter of the universe didn't spread out completely evenly. Rather, it formed vast clumps that would evolve into the galaxies and clusters of galaxies that make up the universe today.
The application of quantum physics to cosmology, to the universe as a whole, was revolutionary. It really changed our entire perception of the evolution of the universe, because it turns out that quantum physics provides a natural mechanism through quantum fluctuations to seed the early universe with small irregularities that would later grow to make galaxies. The thought is really overwhelming. The idea that an object with billions of stars like the Milky Way began life as a quantum fluctuation as what we call a fluctuation of the vacuum, an object of submicroscopic scales. It really is mind-boggling.
It now appears as if the quantum world, the place we once thought of as empty nothingness, has actually shaped everything we see around us.
What happens is something that was a small fluctuation, a tiny quantum mechanical fluctuation, becomes our galaxy, right? Or becomes a cluster of galaxies or whatever, because there's very many quantum fluctuations. So it answers one of the questions we have. Why are there 100 billion galaxies in our viewpoint? Well, in a drop of water, there's many more than 100 billion quantum fluctuations, right? In an atom, there's that many. The vacuum has all this bubbling going on all the time.
The teeming, seething activity of the vacuum, of nothing, and the quantum fluctuations within it were the seeds. Seeds which grew into the universe we see today. This idea gives rise to one final revelation. Today, our best theories about the cosmos tell us that at the beginning of time, the universe sprang from the vacuum, creating not only vast amounts of matter, but also the strange stuff that was predicted by Paul Dirac. Antimatter. But the universe we see today is made of matter. Nearly all of the antimatter seems to have vanished.
According to current theory, the Big Bang produced equal amounts of matter and antimatter, but as the universe cooled down, matter and antimatter annihilated almost perfectly, but not quite. For every billion particles of matter and antimatter, one was left behind. The matter and antimatter that annihilated to produce radiation gave rise to the heat of the Big Bang that we see today in the form of the microwave background radiation. The little particle that was left behind, for every billion that annihilated, is what makes galaxies, stars, planets, and people.
So we're simply the debris of a huge annihilation of matter and antimatter at the beginning of time. The leftovers of an unimaginable explosion. All these insights have arisen from simply trying to understand what nothing really is. What we once thought of as the void now seems to hold within it the deepest mysteries of the entire universe.
In the 400 years or so since Torelli and Pascal began exploring vacuums here on Earth, we've begun to understand in ever greater detail the worlds at the very limits of our perception. And in doing so, we've uncovered the strange truth about reality itself. There's a profound connection between the nothingness from which we originated and the infinite in which we're engulfed.